Step outside on a clear night and look up. Every point of light you see is the past. Not a memory, not a record, not a photograph. The actual past, arriving now, traveling to your eye at the speed of light across distances so large that the journey takes years, centuries, thousands of years, millions of years. When you look at the moon, you see it as it was 1.5 seconds ago. The light now entering your eye left the moon's surface 1.5 seconds before this moment. If the moon were to suddenly vanish, you would not know for 1.5 seconds. When you look at the sun, you see it as it was 8 minutes ago. When you look at Jupiter, you see it as it was between 30 and 50 minutes ago, depending on where the planets are in their orbits. And when you look at Andromeda, the nearest large galaxy to our own, the faint smudge of light visible to the naked eye on a dark autumn night, you are seeing light that left that galaxy 2.5 million years ago. The photons entering your eye tonight were emitted before the first stone tools were made on Earth, before the earliest members of our genus walked upright on the African savanna. You are not seeing Andromeda as it is. You are seeing it as it was, 2.5 million years ago, and there is nothing you can do about this. The delay is built into the nature of light and space. Welcome to Sleepy Science Stories. Tonight we are going to explore what it means that the sky is a time machine, not metaphorically, literally. The night sky is a record of the past at different depths of time, layered like geological strata, with nearby objects showing the recent past and distant objects showing the deep past. Tonight we follow the light. We trace its journeys. We sit with the strangeness of looking out and looking back simultaneously. Let your breathing slow. There is no hurry. The light has been traveling for a long time. It can wait another moment for you to settle. The delay is not a flaw in our instruments. It is not something we can overcome with better technology. It is a fundamental feature of the universe. Light is the fastest thing there is, and even at 300,000 kilometers per second, it takes time to cross the distances between stars and galaxies. This means that the universe, as we observe it, is not a picture of the present. It is a picture of the past at different depths. When you look at the night sky, you are looking through layers of time, stacked on top of each other, each layer corresponding to a different distance and therefore a different age. The nearby layers are recent. The sun 8 minutes ago. The moon 1.5 seconds ago. The stars of our galaxy a few years to a few thousand years ago. The deeper layers are ancient. Andromeda 2.5 million years ago. The galaxies that Webb observes more than 13 billion years ago. The cosmic microwave background, the oldest light of all, nearly 14 billion years ago. You do not need a time machine to see the past. You only need a clear night and a willingness to think about what looking at a star actually means. The universe has been sending you this information your entire life. Tonight we pay attention to what it says. Let your breathing slow. There is no hurry. The ancient light will still be there when you open your eyes again. Light travels at approximately 300,000 kilometers per second. This is fast. It is the fastest anything can travel in the universe. It is fast enough to circle the Earth 7.5 times in 1 second. Fast enough to reach the moon in about 1.25 seconds. Fast enough to reach the sun in about 8 minutes. But space is very large. And when distances become large enough, even light's extraordinary speed becomes something you have to wait for. A light year is the distance light travels in 1 year. It is not a unit of time. It is a unit of distance. 1 light year is approximately 9.5 trillion kilometers. The nearest star to our sun, Proxima Centauri, is about 4.2 light years away. The light you see from Proxima Centauri tonight left that star 4.2 years ago. This seems manageable. 4 years is a comprehensible amount of time. If Proxima Centauri had a planet, and that planet's inhabitants sent us a light signal tonight, we would receive it in about 4 years. We could reply. The round-trip conversation would take about 8.5 years. Long, but not impossible. But the distances in the universe quickly become much larger than 4 light years. The bright star Sirius, the brightest star in the night sky, is about 8.5 light years away. You see it as it was 8.5 years ago. Betelgeuse, the red giant in the shoulder of Orion, is about 700 light years away. The light now entering your eye left Betelgeuse around the year 1325. The 100 Years' War between England and France had not yet begun. The Black Death was still 2 decades away from arriving in Europe, and the Andromeda galaxy is 2.5 million light years away. Light moves fast. Space is larger. The speed of light is not merely a speed, it is a universal constant. It is the same for all observers regardless of how fast they are moving. It is the same whether the light source is approaching you or receding from you. This constancy was what led Einstein to develop special relativity in 1905. If the speed of light is the same for all observers, then other things must vary. Time must pass at different rates for observers moving at different speeds. Distances must contract, mass and energy must be equivalent. The bizarre consequences of special relativity all follow from the single strange fact that light always travels at the same speed. The speed of light is also the speed of causality. Nothing that happens at one point in space can affect something else at another point faster than light can travel between them. A supernova explosion in a distant galaxy cannot affect us until the light from that explosion reaches us. An event in Andromeda today is, for us, causally isolated. We cannot know about it. We cannot be affected by it. The information about it is traveling toward us, but it has not arrived. This is not a problem to be solved. It is the structure of the universe, and the night sky is the most direct possible evidence of that structure, spread out above you every clear night, showing you the past in every direction, at every distance, at every depth of time. The star you see tonight left its light years or centuries or millennia before it reached your eye. You are the destination it was traveling toward, though it did not know it. The light found you in the dark. How do astronomers know how far away things are? This is one of the central problems of observational astronomy, and the answer is a sequence of methods, each building on the last, that astronomers call the cosmic distance ladder. The first rung of the ladder is parallax. Hold your finger in front of your face and close one eye, then the other. Your finger appears to jump against the background. This is parallax. The apparent shift in position depends on the distance to the object and the distance between your two viewpoints. For nearby stars, the Earth's orbit around the Sun provides the two viewpoints. In January, we are on one side of the Sun. In July, we are on the other side, about 300 million kilometers away. By measuring how much a nearby star appears to shift against the background of more distant stars between January and July, astronomers can calculate its distance precisely. This works for stars within a few thousand light years. For more distant stars, astronomers use a type of star called a Cepheid variable. Cepheid variables pulse. They brighten and dim in a regular cycle. The period of that cycle is directly related to the star's true luminosity. By comparing the true luminosity with the apparent brightness, the distance can be calculated. Henrietta Swan Leavitt, a Harvard astronomer working in the early 20th century, discovered this relationship in 1908. Her discovery made it possible to measure distances to other galaxies for the first time. For the most distant objects, astronomers use the redshift of light, the stretching of light waves caused by the expansion of the universe, which we will discuss in more detail later. Each rung of the ladder depends on the rung below it. Each extends the reach of measurement further into the cosmos. The distances we know are built on a chain of reasoning that took more than a century to construct, and each link in that chain was made by careful human observation. The cosmic distance ladder is one of the great achievements of observational astronomy. It took more than a century to build. It required contributions from hundreds of scientists, and it is still being refined because the distances at the top of the ladder, the distances to the most remote galaxies, depend on measurements made lower down, and small errors propagate upward. One of the current tensions in cosmology is called the Hubble tension. When astronomers measure the expansion rate of the universe using the distance ladder, they get a slightly different answer than when they measure it using the cosmic microwave background. The discrepancy is small but statistically significant. It is either an indication that there are errors somewhere in the distance ladder, or that there is new physics waiting to be discovered. This is how science works. The instruments get better. The measurements get more precise. And when precise measurements disagree, it means something important is waiting to be understood. Every rung of the distance ladder is itself a story. The story of the people who conceived the measurement, built the instruments, made the observations, analyzed the data, published the results, had those results criticized, revised them, and eventually saw them accepted. Science is not a list of facts. It is a process conducted by human beings that produces facts through argument and evidence and revision over time. The distances in this story, the light years and the megaparsecs and the look-back times, are not just numbers. They are the accumulated result of that process. They represent what we have learned carefully and collectively about where things are and when their light left them. On a dark night, away from city lights, Andromeda is visible to the naked eye. It appears as a faint smudge, slightly fuzzy compared to the point-like stars around it. It is in the constellation Andromeda, in the northern sky, best seen in autumn. If you know where to look, and your eyes have adjusted to the dark, you can find it without any instrument. What you are seeing is 2.5 million years of travel compressed into a single moment of perception. The photons entering your eye tonight were emitted by stars in the Andromeda galaxy 2.5 million years ago. The galaxy they left looked somewhat different then. 2.5 million years of stellar evolution have changed it. Stars have been born and died. Gas clouds have condensed and exploded. The supermassive black hole at its center has continued to grow. We do not know what Andromeda looks like now, at this moment. We cannot know. The information about its current state will not reach us for 2.5 million years. The Andromeda galaxy is the nearest large galaxy to our own. It is a spiral galaxy, like the Milky Way. It is roughly the same size as the Milky Way, containing perhaps 1 trillion stars. It is approaching us. In approximately 4.5 billion years, the Andromeda galaxy and the Milky Way will collide. Collide is perhaps the wrong word for what happens when two galaxies come together, because galaxies are mostly empty space, and the individual stars almost never actually hit each other. What happens is a gravitational dance, a slow merging over hundreds of millions of years, with the two spiral structures pulling each other apart and eventually coalescing into a single larger irregular galaxy. This collision is coming. We know it is coming because we can measure Andromeda's velocity toward us. It is approaching at about 110 kilometers per second. But what we see when we look at Andromeda is the galaxy as it was 2.5 million years ago. The collision we are calculating is based on that ancient light and what it tells us about the galaxy's position and motion. Look for Andromeda on a dark autumn night. It is northwest of the Great Square of Pegasus. Find the star Alpheratz. The corner star of the square that also belongs to the constellation Andromeda. Follow the chain of stars that extends from Alpheratz toward the northeast. The galaxy is a few degrees north of that chain, roughly where the outer limit of naked eye visibility begins. What you are looking at, when you find it, is the most distant object visible to the naked eye. Everything else visible without a telescope is within the Milky Way, or its satellite galaxies. Andromeda is the one exception. At 2.5 million light-years, it is the only object you can see with your own eyes that is outside our galaxy. The photons reaching your eyes from Andromeda left that galaxy 2.5 million years ago. At that time, the ancestors of our genus, Homo habilis, were using simple stone tools in East Africa. The first stone tools in the archaeological record date to about 3.3 million years ago. 2.5 million years ago, our ancestors were already tool users, but anatomically modern humans would not exist for another 2.5 million years. The light that left Andromeda when Homo habilis was chipping stone on the African savanna has been traveling across the void for all of human prehistory and history, through the entire span of our genus from its beginning to now, arriving tonight, in your eyes, in this moment. That is what it means to look at Andromeda. Every observation in astronomy has what is called a look-back time. The look-back time is how long ago the light was emitted by the object being observed. For the Moon, the look-back time is 1.5 seconds. For the Sun, 8 minutes. For Andromeda, 2.5 million years. For the most distant galaxies that the James Webb Space Telescope has observed, the look-back time approaches 13.8 billion years, close to the age of the universe itself. This means that when astronomers study distant galaxies, they are not studying the present universe. They are studying the universe at different epochs in its history. A galaxy observed with a look-back time of 10 billion years is a galaxy as it was 10 billion years ago, when the universe was much younger and denser and hotter. A galaxy observed with a look-back time of 1 billion years is younger, further along in its evolution. By observing galaxies at different distances, astronomers can trace the history of galaxy formation. They can see how galaxies looked when they were young, when they were middle-aged, when they were mature. The universe is not just spatially vast, it is temporally accessible, meaning that by looking at distant objects, we can observe different eras of cosmic history. The James Webb Space Telescope, launched in 2021, was designed specifically to look back to the earliest epochs of the universe. It observes in the infrared, which is the wavelength to which very distant, very redshifted light has been stretched. Its observations have reached galaxies forming less than 300 million years after the Big Bang. 300 million years after the Big Bang, the universe was about 2% of its current age. The first stars were forming. The first galaxies were assembling. The light from those earliest galaxies has been traveling for more than 13 billion years to reach Webb's mirror. When Webb captures that light, it is not taking a photograph of the distant universe as it is. It is taking a photograph of the distant universe as it was. The look-back time has a direct consequence for what we can and cannot know about the universe. We cannot observe the present state of any object outside our solar system. We cannot observe the current state of the Sun, only its state 8 minutes ago. We cannot observe the current state of any star, any galaxy, any cosmic structure. Everything we observe is the past. This limitation is sometimes called the light cone. In the four-dimensional space-time of relativity, the light cone of an event is the region of space-time that can influence or be influenced by that event, given the constraint that information travels at the speed of light. Events outside the light cone are causally disconnected. They cannot affect us. We cannot affect them. We cannot even know about them until enough time has passed for light to travel between us. The entire observable universe, everything we can see with our telescopes, is the interior of the light cone that began with the Big Bang and has been expanding at the speed of light ever since. Everything outside that cone, the rest of the universe, if it exists, is beyond our reach, beyond our knowledge, beyond our influence. This is a profound kind of isolation. The universe is not connected to itself in the way a room is connected, where everything is present simultaneously. The universe is connected by light, which means it is connected across time. What is present for one part of the universe is past for another. The universe does not share a single moment. It shares only the light that travels between its parts. The look-back time, which sounds like a technical term for an observational detail, is actually a window into something very deep about the structure of reality. Time and space are not separate things. Distance and delay are the same thing. Looking out and looking back are the same thing. When you look at the night sky, you are inside the structure, experiencing it directly, in the only way it can be experienced. Consider what it means that the sunlight warming your skin was emitted 8 minutes ago. The sun is about 150 million kilometers from Earth. Light covers that distance in approximately 8 minutes and 20 seconds. The solar photons that warm your face on a summer afternoon left the sun's surface 8 minutes and 20 seconds before they reached you. But those same photons have a much longer history than 8 minutes. The energy they carry was produced in the sun's core, through the fusion of hydrogen nuclei into helium. This process generates gamma rays, high-energy photons that begin their journey outward from the core. But the sun is very dense. A photon moving through the solar interior is constantly absorbed and re-emitted by atoms in the plasma. It bounces in a random walk through the dense material of the sun, from atom to atom. The average time for a photon to travel from the sun's core to its surface through this random walk is approximately 100,000 years. Some calculations suggest it may be closer to 1 million years. The photon that left the sun 8 minutes ago to warm your skin today may have been produced by a hydrogen fusion reaction 100,000 years ago or longer. At the time it was produced, anatomically modern humans were already present in Africa, but the migration out of Africa that would eventually populate the rest of the world was still in the early stages. The sunlight you feel is ancient in two senses. The photons arrived 8 minutes ago, but they left the sun's core long before the first modern humans walked the earth. The 8-minute delay of sunlight is the most intimate example of the time gap built into astronomical observation. Every time you experience sunlight, you are experiencing something that happened 8 minutes ago. When the sun goes behind a cloud, you do not lose direct sunlight immediately. You lose the stream of photons that left the sun 8 minutes ago and were about to reach you. When the cloud moves, you gain access again to the photons that are just arriving after their 8-minute journey. The process by which photons originate in the sun's core is itself remarkable. Nuclear fusion in the core produces gamma rays, not visible light. These gamma rays are absorbed by the dense plasma of the solar interior within millimeters of where they are produced. They are re-emitted, absorbed again, re-emitted again. Each absorption and re-emission changes the direction of the photon randomly. The photon is doing a random walk through the solar interior, bouncing millions of times. The average distance such a random walk covers in a given number of steps is proportional to the square root of the number of steps. For a photon to diffuse from the center of the sun to the surface by this process takes roughly 100,000 to 1 million years, depending on the details of the calculation. What this means is that the warmth you feel from the sun is ancient in two senses. The photons arrived 8 minutes ago, but the energy they carry was produced by nuclear fusion, perhaps 100,000 years ago. It has been slowly making its way outward through the dense plasma of the sun's interior ever since. The sun you feel on your skin is 100,000 years old and 8 minutes old at the same time. The sun you feel on your skin is ancient in two senses. The photons arrived 8 minutes ago, but the energy they carry was produced in nuclear reactions perhaps 100,000 years ago, before modern humans had fully populated the Earth, before most of the stone tools in the archaeological record were made. Those photons have been making their long, slow, bouncing journey through the solar plasma ever since. And now they are here, on your skin, warming you. The long journey of sunlight ends at you. Betelgeuse is a red supergiant star in the constellation Orion. It is one of the largest and brightest stars visible to the naked eye. It is also one of the most unstable. It is expected to explode as a supernova at some point in the relatively near astronomical future. Near future, for a star, means sometime in the next 100,000 years. Betelgeuse is approximately 700 light-years away. The light we see from Betelgeuse tonight left the star around the year 1325. Here is the question. Has Betelgeuse already exploded? The answer is, we do not know. We cannot know. If Betelgeuse exploded 700 years ago, the light from that explosion has not yet reached us. It is currently traveling toward us at the speed of light and will arrive in our sky as a sudden brightening that could be visible in daylight, brighter than the full moon. If Betelgeuse exploded 2 years ago, the light from the explosion is currently traveling toward us and will arrive in roughly 698 years. If Betelgeuse is still intact right now, at this moment, it will explode at some point in the future. The question of whether Betelgeuse has already exploded has no answer from Earth. Not because we lack the instruments, but because the information cannot reach us faster than the speed of light. The question is not merely unanswered. It is currently unanswerable. This is one of the more mind-bending implications of the finite speed of light. Events happen. The information about those events travels at the speed of light. Until that information arrives, the event might as well not have occurred, from our perspective. The present moment, for distant objects, is a concept that does not have a clear meaning. In late 2019 and early 2020, Betelgeuse dimmed dramatically. It faded more than it ever had in recorded observation. Astronomers called it the Great Dimming. Some wondered if it was about to explode. It did not explode. The dimming was caused by a large amount of stellar material being ejected from the star's surface, which then cooled and formed dust that temporarily blocked part of the star's light from reaching us. But the episode illustrated something important about Betelgeuse. It is a highly variable, dynamically active star. It is genuinely close to the end of its main sequence life. When it does explode, it will be one of the most spectacular astronomical events visible from Earth in recent human history. It will be visible in daylight for weeks. It will be brighter than the full moon at night. The event may have already happened. It may not have happened yet. We are observing Betelgeuse as it was 700 years ago, and our uncertainty about when it will explode, which spans a range of 0 to 100,000 years, means that the explosion may have occurred at any point in that window. There is a version of this story where Betelgeuse exploded 600 years ago. The light is currently traveling toward us, and it will arrive in our sky in about 100 years. The people alive in 100 years will see it happen. From their perspective, Betelgeuse will suddenly flare. From ours, the information about an event that occurred 600 years ago will finally have arrived. The star is 700 light-years away. The events of 700 years ago are happening for us now. The question of whether Betelgeuse has exploded is one of the more beautiful examples of the uncertainty built into astronomical observation. We do not know. We cannot know. The answer is out there, traveling toward us at the speed of light, and we will receive it at some point in the next 100,000 years or so. Until then, we look at Betelgeuse as it was in the 1300s. and we wonder about what it is doing right now, in a place we cannot currently access, 700 light-years away. The oldest light in the universe is not visible to the human eye. It exists everywhere. It comes from every direction equally. It fills all of space. And it is the remnant of an event that occurred 380,000 years after the Big Bang. It is called the cosmic microwave background. In the earliest moments after the Big Bang, the universe was so hot and so dense that matter and energy were intermingled. Photons could not travel freely. They were constantly scattered by the hot plasma of the early universe. The universe was opaque. Light could not propagate. As the universe expanded, it cooled. After about 380,000 years, the temperature dropped low enough for electrons to combine with protons to form neutral hydrogen atoms. This is called recombination. When it happened, the universe became transparent for the first time. Photons could travel freely. The light released at recombination has been traveling ever since. As the universe expanded, the wavelength of this light was stretched, shifted from visible light to microwaves by the expansion of space itself. Today it appears as a faint microwave radiation with a temperature of approximately 2.7 degrees above absolute zero, detectable from everywhere in the sky. When we detect the cosmic microwave background, we are looking at the universe as it was 380,000 years after it began. We are seeing light with a look-back time of approximately 13.5 billion years. The universe's infancy in light. The cosmic microwave background was first detected accidentally by Arno Penzias and Robert Wilson in 1964, using a large radio antenna built for communications purposes. They noticed an unexplained noise in their instrument, a faint signal that seemed to come from everywhere equally. After exhausting all mundane explanations, including cleaning pigeon droppings from the antenna, they concluded that the signal was real. It was the oldest light in the universe, detected as unwanted noise by two engineers trying to point a radio antenna at a communications satellite. The cosmic microwave background is not just an ancient signal. It is a detailed map. The temperature of the cosmic microwave background is not perfectly uniform. There are tiny fluctuations, variations in temperature of about 1 part in 100,000. These fluctuations were imprinted on the background at the time of recombination, and they carry information about the distribution of matter in the early universe. The regions that were slightly denser than average attracted more matter. Over time, gravity amplified the initial density fluctuations, and the regions that were slightly denser became the seeds of the large-scale structure of the universe. The galaxy clusters and superclusters and cosmic filaments that we observe today grew from those tiny temperature fluctuations in the cosmic microwave background. When we map the cosmic microwave background in detail, as the COBE satellite did in the early 90s, as the WMAP satellite did in the 2000s, and as the Planck satellite did in the 2010s, we are not just measuring an ancient signal. We are reading the initial conditions of the universe. We are seeing the seeds of every galaxy that ever formed, including the Milky Way, including the Sun, including the Earth. The cosmic microwave background contains, in its pattern of temperature fluctuations, the information that determined why the universe looks the way it does. It is the universe's birth certificate, and it is visible all around us, in every direction, as a faint hiss of microwave radiation that fills all of space, detectable with the right instruments, present in the noise of every radio receiver, arriving from the edge of the observable universe 13.5 billion years after it was emitted. In 1929, Edwin Hubble published a paper showing that distant galaxies were moving away from us. Not just moving away faster the farther they were. A galaxy twice as far away was receding twice as fast. This relationship is now called Hubble's law. The evidence for this came from redshift. When a light source is moving away from you, the wavelength of its light is stretched. The light is shifted toward the red end of the spectrum. The faster the source is moving away, the larger the redshift. By measuring the redshift of galaxies and combining it with their known distance, Hubble showed that the universe was expanding. This discovery changed everything. If the universe is expanding now, it was smaller in the past. Running the expansion backward in time leads to a point where everything was concentrated in an extremely small, extremely hot, extremely dense state. The Big Bang. The redshift of distant galaxies means something important for the light we receive from them. The light was emitted at a certain wavelength, but as it traveled through expanding space, the space itself stretched, and the wavelength of the light stretched with it. Light from a galaxy 10 billion light-years away was emitted in the ultraviolet, but arrives as infrared, stretched by the expansion of space during the 10 billion years of the journey. This is why the James Webb Space Telescope observes in infrared. The most distant galaxies, emitting light when the universe was young, have their light redshifted into the infrared by the expansion of space over billions of years. To see the early universe, you need a telescope that can see infrared light. Redshift also means that the look-back time and the current distance of distant objects are not the same. A galaxy that we observe with a look-back time of 10 billion years is not 10 billion light-years away today. In the 10 billion years since the light was emitted, space has continued to expand, and the galaxy is now much farther away than 10 billion light-years. The expansion of the universe is not the expansion of matter into empty space. It is the expansion of space itself. This is a subtle but important distinction. When we say the universe is expanding, we do not mean that galaxies are flying outward from a central point like shrapnel from an explosion. We mean that the space between galaxies is increasing. Every point in space is moving away from every other point, not because things are moving through space, but because space itself is growing. An analogy often used is dots on the surface of a balloon that is being inflated. As the balloon expands, every dot moves away from every other dot. There is no center. There is no edge. Every dot is equally the center from its own perspective. The universe expands in the same way, in 3 dimensions rather than 2. The expansion of space has a strange implication. Very distant galaxies are receding from us faster than the speed of light. Not because they are moving through space faster than light, which would violate relativity, but because so much space is expanding between us and them that the total rate of recession exceeds the speed of light. These galaxies are beyond what is called the Hubble sphere. We cannot receive light from them. They are permanently beyond our observational horizon. This means that the observable universe is not just a snapshot of the past. It is a snapshot of the past that is slowly shrinking. As the universe expands, more and more of the distant universe accelerates beyond our ability to observe it. In the very distant future, the only galaxies we will be able to see are those within our own local group, the Milky Way and its immediate neighbors. The rest of the universe will have receded beyond the horizon. Many of the stars you see in the night sky no longer exist. Stars are not permanent. They are born from clouds of gas. They live for millions or billions of years, fusing hydrogen in their cores. And then they die, in ways that depend on their mass. Low-mass stars like the Sun will eventually exhaust their hydrogen fuel and expand into red giants before shedding their outer layers as a planetary nebula and leaving a white dwarf. The Sun has about 5 billion years of main sequence life remaining. High-mass stars live shorter lives and die more dramatically. A star 10 times the mass of the sun might live for only a few tens of millions of years. When it dies, the core collapses in a fraction of a second, and the outer layers are expelled in a supernova explosion. What remains is either a neutron star or, for the most massive stars, a black hole. The stars visible in the night sky range in distance from a few light years to several thousand light years. The light from the more distant ones left thousands of years ago. In thousands of years, a massive star can exhaust its fuel and explode. Some of the bright stars you see tonight have already died. The supernova that ended them occurred years or centuries or millennia ago, but the news has not arrived yet. The light from the explosion is traveling toward us at the speed of light and will arrive at some future date, appearing suddenly as a new bright star in the sky. We do not know which stars these are. We do not know which of the points of light you see tonight are already gone. We are looking at a snapshot that is not synchronized. Nearby stars are shown as they were recently. Distant stars are shown as they were long ago. The sky is not a picture of now. It is a picture of many different nows, all shown simultaneously, all arriving at your eye in the same moment from different depths of the past. The uncertainty about which stars are already dead creates a strange relationship with the night sky. You look up and you see a sky that appears fixed. The constellations look the same tonight as they looked to your grandparents, as they looked to people 2,000 years ago. The sky seems permanent, eternal, unchanging. But this apparent permanence is an illusion created by our short timescale. The sky does change. Stars move. Stars die. New stars are born. The changes are slow by human standards, but they are constant. The constellation Orion, which appears in the northern winter sky, will be unrecognizable in 100,000 years. The stars that form it are not gravitationally bound to each other. They are moving in different directions through the galaxy, and over hundreds of thousands of years, those different motions will carry them apart until the pattern we recognize as Orion no longer exists. Several of Orion's bright stars are expected to explode as supernovae within the next million years. When they do, they will briefly outshine all the other stars in the sky. Then they will fade. The constellation will be changed. The sky is not a painting. It is a process. And because the process is slow, we see only a single frame of it, frozen by our short lives, appearing to us as fixed and eternal, because we do not live long enough to see the next frame. The ancient light in the sky is carrying messages about that process. Each photon is a data point in a story that spans billions of years. We have access to only a small slice of that story, but even that small slice reveals something remarkable about the nature of the universe we inhabit. No telescope has yet observed an individual star from the very first generation of stars. The first stars formed within a few 100 million years of the Big Bang. They were very different from the stars that exist today. The early universe contained almost no elements heavier than hydrogen and helium. The first stars were formed entirely from these two elements, with tiny traces of lithium. Without heavier elements, the first stars could not be like the Sun. They could not form planetary systems around them. They could not even form in the same way, because the heavier elements that modern stars use to cool and fragment their gas clouds into smaller pieces were not present. The first stars are thought to have been enormous, perhaps hundreds of times the mass of the Sun. They lived brief, violent lives, burning through their fuel in a few million years and exploding as supernova. Those supernovae produced the first heavy elements, carbon and oxygen, and nitrogen, and silicon and iron, and scattered them into the space around them. From those scattered heavy elements, the second generation of stars formed, and from the debris of those stars, the third generation, and so on. through many cycles of stellar birth and death, until the interstellar medium contained enough heavy elements to produce small stars like the Sun, with rocky planets, with liquid water, with the chemistry that eventually produced life. We are, in a literal sense, made of stardust. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of these elements were forged in the nuclear furnaces of ancient stars and scattered by their deaths. We are the product of billions of years of stellar recycling. The light from those first stars has been traveling since long before the Earth existed. Some of it has been so redshifted by the expansion of the universe that it is only detectable with the most sensitive infrared instruments ever built. The first stars are sometimes called population the third stars, using an astronomical naming convention in which the youngest stars are population I, older stars are population the second, and the hypothetical first generation is population no population the third star has been definitively detected, because they are expected to be so massive and so luminous that they would have been extremely short-lived, burning out in a few million years and exploding as supernovae long before the present day. Their light, redshifted enormously by the expansion of the universe over more than 13 billion years, is difficult to separate from other faint signals. But the James Webb Space Telescope has been searching for their signatures, and in 2023 announced possible evidence for population the third stars in a distant galaxy cluster. The announcement was tentative, subject to follow-up observation, but it opened the possibility of directly observing the first generation of stars that seeded the universe with heavy elements. We are made of those elements. The carbon and oxygen and nitrogen and iron that constitute us were forged in the nuclear furnaces of ancient stars and scattered by their deaths. We are, in the most literal sense, products of stellar alchemy. The universe organized hydrogen into stars. The stars organized hydrogen and helium into heavier elements. Those heavier elements were scattered into space. Space organized them into new stars and planets, and on at least one planet, chemistry organized them into life that eventually looked back at the stars and wondered where it came from. The answer, encoded in the ancient light of the night sky, is from there, from those stars, from that light, from the same processes, playing out over billions of years, that produced the photons entering your eye tonight. The universe is not infinite, or if it is, we cannot observe the infinite part. There is a limit to how far we can see. It is called the cosmological horizon, or the Hubble radius. It is the distance from which light has had time to reach us since the Big Bang. Since the universe is approximately 13.8 billion years old, and light has been traveling since the earliest moments, you might expect the cosmological horizon to be about 13.8 billion light years. But the universe has been expanding. The regions of space that emitted the light we are now receiving were much closer to us when they emitted it. In the time since the light was emitted, those regions have moved much farther away because of the expansion of space. The observable universe, accounting for this expansion, has a radius of approximately 46 billion light years. Beyond the cosmological horizon, the universe continues. We have no way of knowing what is there, or even whether the universe is the same beyond the horizon as it is within it. The cosmological horizon is not a wall or a boundary in space. It is the limit of what information can reach us given the age of the universe. The observable universe contains approximately 2 trillion galaxies. This number was revised upward dramatically in 2016, when a new analysis of deep field images suggested that previous surveys had been observing only the largest, brightest galaxies and missing many smaller, fainter ones. 2 trillion galaxies, each containing hundreds of billions of stars, most of those stars potentially accompanied by planets. The scale is not possible to hold as an intuition. It can only be held as a number. 2 trillion galaxies, and the light from all of them is old. The nearest is 2.5 million years old. The most distant is over 13 billion years old. The number 2 trillion galaxies, the current estimate for the number of galaxies in the observable universe, is difficult to hold as a human intuition. Consider that our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. Most of those stars are likely accompanied by planets. The Milky Way alone probably contains more planets than there are grains of sand on all the beaches of Earth. Now multiply that by 2 trillion. The number of stars in the observable universe is approximately 10 to the power of 24. That is 1 followed by 24 zeros. For comparison, the number of grains of sand on all of Earth's beaches is estimated at around 10 to the power of 19. There are roughly 100,000 times more stars in the observable universe than there are grains of sand on Earth. And beyond the observable universe, the universe continues. We do not know how large the total universe is. It might be infinite. The current measurements of the cosmic microwave background suggest that the overall curvature of the universe is very close to flat, which is consistent with an infinite universe, though it does not prove it. The observable universe is a sphere of light and matter and time that surrounds us, defined by the distance light has traveled in the age of the universe. It is enormous beyond anything our intuition is equipped to handle. And it is just the part we can see. The night sky that you look up at on a clear night shows you a tiny fraction of even the observable universe. Most of it is below the horizon. Most of it requires a telescope to see. Most of it is beyond any telescope ever built or planned. But the fraction visible to the naked eye is enough to give you a sense of the scale, enough to feel, on a clear dark night, that you are something very small inside something very large, and that the large thing is very old. There is something philosophically strange about the Andromeda galaxy. You can see it with your naked eye. You can look at it right now. It is there, in the sky, visible. You are receiving information from it this instant. But what you are receiving is not information about what is happening there now. The light entering your eye left Andromeda 2.5 million years ago. Whatever you are learning from it, you are learning about the past. The state of Andromeda right now, at this moment, is unknown to you and will remain unknown for 2.5 million years. In some philosophical traditions, the present moment is the only real moment. The past exists only in memory, the future only in anticipation. But the present is here, now. For objects at astronomical distances, the present does not exist for us in this sense. When we observe Andromeda, we are not observing its present. We are observing its past. The present of Andromeda is inaccessible. It is happening, right now, 2.5 million light years away, and we will not have any information about it for 2.5 million years. This is not a limitation of our instruments. It is a fundamental feature of the universe. Information cannot travel faster than light. The present state of distant objects is, by physical necessity, unknowable. The philosopher who coined the phrase the eternal present would have found the cosmos deeply inconvenient. The universe does not offer a single shared present moment. What is now for us is 2.5 million years ago for Andromeda, and for Andromeda, what is now is 2.5 million years in what we would call the future. There is no cosmic now. There is only here and now, and the echoes of other nows arriving at different delays. The Andromeda paradox extends to every observation in astronomy. When we image a galaxy 10 billion light years away with the James Webb Space Telescope, we are not learning about that galaxy as it is. We are learning about that galaxy as it was 10 billion years ago. If astronomers in that galaxy were, 10 billion years ago, building telescopes to observe us, they would see the Earth as it was 10 billion years ago, before complex life existed, covered in microbial mats, with an atmosphere containing little oxygen. The universe we observe is not the universe as it is. It is the universe as it was, at different times, stacked on top of each other in our telescopes. The nearby universe is shown as it was recently. The distant universe is shown as it was long ago. This means that the universe we observe is not a snapshot but a history. And it is a particularly unusual kind of history, because we can access it directly. We do not need to infer what the early universe was like from indirect evidence. We can observe it. We can point a telescope at a distant galaxy and see, directly, what galaxies looked like 12 billion years ago. The night sky is not a window. It is a time machine. Not a metaphorical time machine, but a literal one, in that it allows access to the past through direct observation. The past is not gone. The past is still arriving. Every night, ancient light completes journeys that began before the Earth existed, and some of it reaches you, carrying information about what was happening in distant parts of the universe before your species, before your planet, before your star existed. This is not a small thing. It is one of the stranger and more remarkable features of the universe we inhabit. If there is life elsewhere in the universe, the delay of light has a profound implication for how we might know about it. The nearest star system to our own, the Alpha Centauri system, is about 4.25 light years away. If there is an inhabited planet there and its inhabitants decided to send us a signal tonight, we would receive it in about 4.25 years. We could reply. The conversation would take about 8.5 years per round trip. This is manageable, in principle. Over centuries, a real exchange of information could occur, but the nearest star system to our own is exceptional in its closeness. The vast majority of stars in the galaxy are much farther away. The average distance between stars in the Milky Way is several light years in the neighborhood of the Sun, and larger elsewhere. A signal from a civilization on the other side of the galaxy would take 50,000 years to arrive. The SETI program, the search for extraterrestrial intelligence, has been listening for signals from other civilizations for decades. So far, it has heard nothing definitive. The Great Silence, as it is called, may mean many things. It may mean there are no other civilizations. It may mean they are using communication methods we have not thought to listen for. It may simply mean that in the vast distances of the galaxy, signals have not had time to reach us yet. Carl Sagan, who thought deeply about these questions, pointed out that the universe is very old and very large, and that the absence of signals so far is not evidence of the absence of civilizations. It is evidence that we have been listening for a very short time in a very small part of a very large universe. If there is a civilization sending signals right now on a planet orbiting a star 50,000 light-years away, those signals are traveling toward us at the speed of light. They will arrive in 50,000 years. We will not be the same civilization that we are now, if we still exist at all. The message will reach our descendants, or our ruins, or the species that comes after us. The light connects. But the connection takes time. The implications of the light speed delay for any possible cosmic civilization are profound. Even within our own galaxy, the Milky Way, the distances are such that any communication would require timescales longer than human history. A civilization on the other side of the galaxy, 50,000 light-years away, might be broadcasting signals right now that will not reach us for 50,000 years. By the time those signals arrived, whatever civilization received them would have had 50,000 years of history since the signals were sent. The senders might no longer exist. The receivers, if they exist at all, would be the descendants of many generations of whatever we currently are. This is not depressing. It is simply the structure of reality at cosmic scales. The universe is organized so that neighboring stars can, in principle, communicate over timescales of years or decades. But the galaxy is so large that true galactic civilization, if it exists, would operate on timescales of thousands or millions of years. Frank Drake, who founded the SETI program in the 1960s, developed an equation for estimating the number of communicating civilizations in the galaxy. The Drake equation accounts for the rate of star formation, the fraction of stars with planets, the fraction of those planets that develop life, the fraction of those that develop intelligent life, the fraction of those that develop communication, and the average lifetime of a communicating civilization. The critical variable is the last one: lifetime. If civilizations on average survive for only a few hundred years of technological development before destroying themselves or collapsing, there may be very few, if any, communicating civilizations in the galaxy at any given time. If civilizations survive for millions of years, the galaxy might be full of them. We do not know which is true. We are, so far, the only data point. The night sky is not just beautiful. It is an archive. Every photon that reaches your eye from the night sky carries information about the object that emitted it and about the space that photon traveled through. The wavelength carries information about the temperature and composition of the emitting object. The polarization carries information about magnetic fields the photon passed through. The timing of arrival carries information about the distance and the age of the source. By measuring these properties carefully, astronomers have reconstructed the history of the universe from the evidence encoded in the light that has reached us. The history begins with the cosmic microwave background, the oldest light carrying information about the state of the universe 380,000 years after the Big Bang. It continues through the light from the first galaxies, observed at look-back times of 13 billion years, showing the universe in its infancy. It continues through galaxies at intermediate distances, showing the universe at various stages of its maturation. And it ends, for now, with the nearby objects, the planets and moons and asteroids of our solar system, the stars of the Milky Way, the Magellanic Clouds, and Andromeda, the faint smudge visible to the naked eye, the closest large galaxy, showing us what 2.5 million years ago looked like. The archive is complete, in the sense that it contains every photon that has reached us from the beginning of the cosmos. But it is also limited. It shows us only what has already happened, at the delay imposed by the speed of light. It shows us only what emitted light in our direction. It shows us only what traveled through intervening matter, without being absorbed. But within those limits, it is the most complete record of the history of the universe that nature has provided. The night sky, dark and cold and full of ancient light, is the universe remembering itself. The night sky has been read as an archive by every civilization that has looked at it carefully. The ancient Babylonians tracked the movements of the planets across the sky over centuries, building up records that allowed them to predict eclipses and planetary conjunctions. Their records were so accurate that modern astronomers have used them to reconstruct the positions of planets thousands of years ago. The ancient Chinese astronomical records include observations of supernovae, novae, and comets that modern astronomers have identified with specific objects. The guest star observed in 1054 CE, recorded by Chinese, Japanese, and Native American observers, is now known to be the supernova that created the Crab Nebula, a remnant visible today with a small telescope. Islamic astronomers of the medieval period built on the Greek astronomical tradition and extended it. They named many of the stars still known by their Arabic names. They developed mathematical techniques that made the calculation of planetary positions more precise. The European astronomical tradition, from Copernicus through Galileo, through Newton, through Herschel and beyond, progressively revealed the structure of the solar system, the nature of stars, the size of the galaxy, and eventually the scale of the cosmos. Each generation read the archive differently, with different instruments and different mathematical tools and different conceptual frameworks. Each generation extended the reach of what could be known from the ancient light. And the archive itself did not change. The same photons that fell on the eyes of Babylonian astronomers 4,000 years ago, falling from the same stars by the same physics, continue to fall on our eyes tonight. The archive is patient. It has been there all along, waiting for us to learn how to read it. Lie still for a moment. The atoms in your body were made in stars. The hydrogen, the most abundant element in you, was made in the first minutes after the Big Bang, in the heat of the early universe. It has been hydrogen for nearly 14 billion years. The carbon in your cells was forged in the cores of red giant stars through the triple alpha process, a nuclear reaction in which 3 helium nuclei combine to form 1 carbon nucleus. Those stars lived and died before the sun was born. Their cores exploded in supernovae. Their carbon was scattered into the interstellar medium. That carbon became part of the gas cloud that collapsed to form the sun and the planets. It became part of the Earth. It became part of the organisms that lived on the Earth for billions of years before you existed. And eventually, through the long chain of chemistry and biology and evolution, it became part of you. The oxygen you breathe was made in the same stellar processes as the carbon. The iron in your blood was made in the final moments of a massive star's life, forged in the extreme heat of a collapsing stellar core and scattered by the supernova that followed. You are not separate from the universe. You are a part of it. A part that has temporarily assembled itself into a form complex enough to perceive and wonder about the rest. When you look at the night sky, you are ancient light looking at ancient light. The photons entering your eye traveled for millions or billions of years. The atoms in your eyes have their own ancient history, forged in stars that died before the Earth existed. The recognition that occurs when you look at a distant galaxy is, in some sense, the universe recognizing itself. The star Betelgeuse, 700 light-years away, may already be gone. Andromeda, 2.5 million light-years away, has been changing for 2.5 million years without your knowledge. The cosmic microwave background, filling the sky in all directions, is the remnant of a universe that was 13 billion years younger than this one. And you are here, in this moment, lying in the dark, made of stardust, looking up at time. The sky is very old. And so, in a certain sense, are you. Sleep well. The ancient light will still be there tomorrow. The night sky above you contains all of this. The moon 1.5 seconds away. The sun 8 minutes away. The nearest stars a few light years. The stars you can see with the naked eye, ranging from a few light years to a few thousand light years, showing you the Milky Way as it was from a few years to a few thousand years ago. Andromeda, 2.5 million light years away, showing you what 2.5 million years ago looked like, before your species existed. Galaxies visible with a small telescope at distances of tens of millions of light years, showing you the universe as it was before multicellular life appeared on Earth. Galaxies visible with large telescopes at distances of billions of light years, showing you the universe as it was before the Earth formed. And the cosmic microwave background, the oldest light of all, filling the sky in every direction, carrying information from 380,000 years after the Big Bang. All of this is arriving simultaneously, in this moment, as you lie still and breathe. You are at the center of a sphere of ancient light that extends in every direction, deeper and older the farther you look. A record of the universe's history written in photons and carried across inconceivable distances to reach this single point, this moment, your eyes. The star you came from. the galaxy that contains your star, the universe that contains your galaxy. All of it sending you its ancient light. All of it saying, in the only language the universe speaks, I was here, long ago. This is what I looked like. And now the light of my past has found you, in your present, on your small planet, in your brief and improbable moment of existence. Sleep well. The ancient light will still be there tomorrow.